Silicon is the second chemical in the Earth's crust by dispersion. Quartz is usually mined from natural deposits. Metallurgical silicon is obtained in an arc furnace at an average temperature of 1800 degrees centigrade. Trichlorosilane is obtained by chlorination of silicon at a temperature of 260 to 4000 degrees centigrade. Purification of TCS from admixtures, boron, phosphorus and carbon is conducted via rectification. Polysilicon crystalline is obtained by depositing and crystallizing polysilicon from various gaseous silanes at heated silicon filaments in the hydrogen atmosphere inside CVD reactors. filament quality determines the grade of deposited polysilicon and the success rate of the deposition process. A polysilicon ingot is fixed in a loading chamber. Then it is brought to the inductor, where it is heated to the melting temperature. Melted silicon is placed on a quartz draw hole. The seed rod, made of polycrystalline silicon, is delivered into the melt through a chilling bath and a hole from below the chamber. The mobile mechanism draws the seed with the melted silicon down during a continuous production process. 2 filaments can be obtained from a single ingot. Our unique method allows for filling the obtained filament with thermodonors that give the resistivity shown in the table without deteriorating the end product's quality.
IM Flash manufactures its NAND flash chips in a state-of-the-art 300mm clean room. Manufacturing a semiconductor is much like building a skyscraper. At the foundation is a bare silicon wafer. Circuitry is built upon this wafer layer by layer to form the microscopic components in each NAND memory device. But this construction isn't 20 stories tall. Try 20 nanometers, or 5,000 times smaller than the diameter of a human hair. Each layer in a NAND flash device is formed through a series of steps or processes. And each of these processes is conducted at different machines or tools. For this reason, IM Flash utilizes a state-of-the-art, fully automated material handling system to transport wafers from machine to machine with increased efficiency. The first step is to deposit a uniform layer of materials on the wafer from which the circuit pattern will be built. Next, the wafer is coated with a layer of photosensitive resist. Like film in a camera, the resist layer is then exposed by passing ultraviolet light through a special quartz negative called a reticle. Once developed, the exposed areas of resist are removed, and a high-energy plasma gas is used to etch the pattern of the circuitry. Following the etching process, the surface is cleaned by immersing the wafers in a chemical bath. Then, exposed areas of the wafer are bombarded with ions to change the conductivity of the silicon. This process creates the actual electronic components in the NAND device. To ensure uniformity, each wafer is polished to a perfectly smooth surface. Finally, a layer of metals is deposited on the wafer to create the electronic pathways that interconnect the tiny components in each device. This whole series of steps is then repeated more than 20 times to build the complex layers needed to manufacture a flash memory device. Once the wafer has been processed, individual NAND flash or die are placed on circuit boards. Each die is encapsulated in a protective plastic package and tested for speed and performance. Finished NAND flash chips are then integrated into a wide variety of today's memory-rich products, and in turn, put a world of information in the palm of our hands.